Thank you very much for the invitation, of course, to have the opportunity to speak today. The topic that I'll be talking about today is one of my favorites. It's about various concepts of constructions, Euclidean constructions, and specifically triangle constructions. This is something that I really enjoy. I work a lot in this area, in related areas, and I hope that you will find everything that I have to tell you today to be interesting. First of all, I'm going to share my screen here. That's a little bit much. There we go. And now I have this presentation prepared. This presentation is only for the very first part of the talk. Afterwards, I will be actually doing some constructions on screen. They will be slightly unusual constructions, I hope, and I hope that there will be something new and interesting for everyone. I understand that the level of understanding of you all is a bit varied. So I can imagine that maybe some of the things that I will be assuming as being known will be very well known to some of you and maybe less so for others. So maybe we should just jump right in, and I will explain what the concepts are that I will be assuming as well known so that we can actually do the constructions, and also what types of constructions we'll be looking at. If there is some information needed in something, of course, there is plenty of information available anywhere. And if there's something specific that you would like to know, of course, we can talk about this at the end. So first of all, we will be talking about specifically Euclidean constructions. So that means that we're talking about constructions using a straight edge and a compass. So with a straight edge, we have the opportunity in the classical idea of connecting 2 points. We can either draw a line segment joining 2 points, or we can draw the line, we can extend the line segment. And with a compass, we can draw a circle if we are given a point and a radius. That radius could be given as 2 points, or it could be given as the length of the line segment. Either way, we have those two constructions that are possible in Euclidean concepts and nothing else. Everything else must be reducible to these ideas, and of course then finding new points through intersections of either lines or line segments or circles or arcs of circles. There's nothing else possible. In order to construct triangles, we will need to introduce or use the concept of triangle determinants. We know that if we are given the 3 sides, the lengths of the 3 sides of a triangle, for instance, we can certainly draw the triangle uniquely, with the exception of translations or reflections in the plane. So whenever we talk about a unique construction, we're always assuming that we are not talking about the spot where we are drawing a triangle or constructing the triangle. But typically, because we have this idea of having 3 sides given, and of course, related to that, we have other opportunities where we can have, or other options where we can have 3 things given, whatever that might be, 3 determinants given. We will find that in general, having 3 determinants of a triangle given will determine the triangle if it's at all possible to construct such a thing. And there are various options. If we have a look at a typical triangle and various things that are associated with the triangle, there can be lengths of various line segments, or they can be angles that are the determinants, and there are some various options that we have. I've already mentioned the concepts of the lengths of the sides of the triangle. So if we have a triangle with vertices ABC, we can have the lengths of the sides A, B, or C. We could have the angles, the internal angles of the triangle that could be given. So the angle alpha in A, beta in B, gamma in C. I'm using notation here that is the notation that I'm used to. I'm aware that notation of this type is not completely unique to everywhere or not, let's say completely uniformly used in every culture. So I hope that if some of the things that I'm using here are not what you're used to, that you will still understand what types of determinants I'm talking about in the context. Then slightly more sophisticated is if we start using things like the altitudes of a triangle, lengths of the line segments that we get by determining the perpendicular from a vertex of the triangle to the opposite side, to the base point. Then the medians, of course, the line segments joining the vertices to the midpoints of the opposite sides. Those are also quite interesting determinants that we can give. Lengths of the angle bisectors. The angle bisectors in this case are not the lines or the rays, but rather here we're talking about the lengths of the line segments joining the vertices with the points in which the angle bisectors as lines intersect with the opposite sides. And then we also have the in radius of the circle, which I've denoted here by rho. Again, this is something that's not always the same, but I've tried to stick to rho here for the in radius. Then there's also the concept of the x radii. I haven't included that here in this drawing because it would be slightly bigger, but I'll have a picture of the x radii in a second. Those are, of course, also the radii of the circles that are tangent to all three sides of the triangle, but externally tangent to one of the sides and internally tangent to the extensions of the other two sides beyond the vertices. And then there's also the circumradius, so the radius of the circumcircle. All of these things are interesting determinants, and it turns out that if we choose more or less any three of these things, and there are a lot, obviously, we can construct triangles from these three determinants. Now, there are some cases where things are not possible with Euclidean methods. There are some very obscure combinations of these things that we can try that simply don't work. There are some combinations that aren't unique. For instance, it's fairly well known if we choose all three of the internal angles of a circle, we aren't going to get unique triangles, because as soon as we choose two triangles, we already two internal angles, we already know the size of the third angle, because the sum of the angles in the triangle is always going to be 180 degrees. So that's redundant information, and that can't be something that can be used to get similar triangles with these three angles. So that's not going to work either. But there are some standard constructions that I think are standard everywhere. Everyone knows how to construct a triangle from lengths of, if the lengths of the three sides are given. I think everyone knows if we are given the lengths of two sides and the size of the contained angle. So things like that are fairly well known. But then there are other combinations of triangle determinants that we can use, where finding a possible construction with Euclidean methods is not at all trivial. And actually, I find quite interesting, because finding these constructions requires the use of some fairly sophisticated tools in Euclidean geometry. And I have a few of the tools listed that I'm going to be using in the constructions today coming up here. So the first useful tools that we're going to be talking about, and I hope that these are familiar to you. I would guess those of you who have done this for a while and are familiar with Euclidean geometry and methods of Euclidean geometry will know these things very well, but for others maybe not so much. This is something that's worthwhile learning anyway, whether we're doing constructions or not. So first of all, we have the concept of the incircle of a triangle. Of course, the incenter is the point in which the inner angle bisectors intersect, and we have the in radius, which is of course the common length of the perpendiculars that we can drop from the incenter to the sides. That's fairly obvious. But then we also have the concept of the three x circles that I was just talking about earlier. This picture here has a lot of information that we don't really need right now. What we need right now, and what will be a useful tool in our constructions, is simply the idea that we can determine the centers of the x circles, the x centers, also by constructing the angle bisectors between the sides. But in the case of the x-centers, we aren't finding the common points of all three internal angle bisectors, but rather the common point of one of the internal bisectors and two of the external bisectors. And since the external bisectors are always perpendicular to the internal bisectors, we will be using these right angles as well. So that's one of the quite useful tools that we will be applying here when we're talking about in radii and x radii of triangles and doing constructions using those. Then the next set of useful tools is anything that has to do with the angle subtended by an arc on a circle. So of course, if we have the diameter of a circle, then we know that the angle subtended by the diameter from any point on the arc is always a right angle. Here it's just denoted by alpha and beta. So alpha plus beta is always a right angle, of course. And this, generalizing this, we know that for any point A on the greater arc determined by the 2 points B and C, by the chord BC, the sum of the two angles x and y that are mentioned here is always equal. It's always half of the angle subtended at the center. So that's why we have a 2 phi there. Of course, that also holds if the point A is such that the circumcenter is not in the interior of this circle. And the same angle also turns up if we draw the tangent to the circle at the endpoint of one of the radii, either in B or in C, between the tangent and the chord BC. It's the same angle as the angle and it's subtended at the arc. So that's also a very useful tool that we'll be using. I assume, or I hope that these things are well known, and if not, that's the kind of thing that everyone should know if you are doing, of course, competition geometry problems and things like that. Then the next useful tool that I have here is what happens with the centroid of a triangle. A centroid as the common point of the okay, no, I've forgotten the English term right now, but of the lines joining the vertices to the midpoints of the opposite sides. The centroid, here it's called S in the triangle ABC. That's because it's the short form for the German word, but otherwise we don't have to worry too much about these things. There's a special information that's contained in here, namely that this point S will always divide the line joining the vertex to the midpoint of the opposite side in sections in the of which the longest section is always twice the length of the shortest. So the distance from the vertex to S is always twice that of the distance from S to the midpoint of the opposite side. The reason for that is contained in this drawing here. If we simply add the triangle a second time, then of course we can simply use similar triangles and obtain various line segments of the same length. And so we immediately obtain that this special property is holds for the centroid. That's also something that we'll be using in one of our constructions. Then another interesting tool is something, this is in Austrian culture, we call this the South Pole Theorem. I'm aware that this is something that's very Austrian. This is not something that's normally known by this name in other cultures, not even in other German-speaking countries, interestingly enough. But it's a very useful topic. If you have a look at the triangle ABC in this last drawing that we have here, it's fairly obvious that the angle bisector of the inner angle bisector of the triangle ABC in C will intersect the bisector of the chord AB in a point that is called SC here, and that lies on the circumcircle of the triangle ABC. In our way of speaking here, but this is a national work that we have, we call this the south pole of the circle. The fact that they actually intersect here simply has to do with the fact that we have equal angles, once again, from chords of equal length or arcs of equal length on this circle. So it's actually quite an obvious fact. And associated with the South Pole, we also have a North Pole, the point that's known here as NC, which is also up there, which of course is the common point of the bisector of AB with the external angle bisector of ABC. So that will also be proved to be useful when we're doing constructions with X centers and things like that. And finally, there's a little special case that we have here. If we have a look at this point SC that we're talking about, that I just called the South Pole of the circle, but of course you don't need to call it that. That is the center of a circle that passes through the endpoints of the chord through A and B. And this circle also passes through the incenter of the circle ABC. That's also something that we will be using. Not difficult to prove at all, just something where you have to take a look at the angles and do a bit of highly elementary calculation in case you've never seen this before. But of course, it's a fact that is quite well known to anyone who is proficient in Euclidean proofs and proofs in elementary plane Euclidean geometry. So that is where we are right now with the tools that we will be using. I will be giving you some more information later on, but now I think we can leave this presentation here. We'll be talking about this later on. And right now I'd like to start with the first construction. And the first construction that I have here is one to start off with something that I think is already quite interesting, but that is not too difficult yet, and that I think can be discovered if you just are aware that this is a topic. We're given the length of a side C in a triangle, so that's the length of the side AB. I've prepared these things here so that this is all in GeoGebra, so I'll be doing the constructions here in GeoGebra as well. But the way I've prepared it is that I've just made a small picture here in the corner showing what is given. The red line segments are what is given. Also, there'll be angles in some of the problems. And so we're given this side C, and we're also given two of the altitudes of the triangle. You have the altitude HA, which is the altitude through the vertex A, and the altitude HC, which is the altitude through the vertex C. The reason that they're called H, that's simply another thing that's derived from the German name, because in German the altitude is a Höhe and it starts with H. Again, I hope that's not something that will irritate anybody too much that I've named the altitudes H, but these are drawings that I already had, so I wanted to just use the same notation also for other parts. That's the only reason that I kept this. So we want to construct a triangle ABC, of which we know the three the lengths of the three line segments C, HA, and HC. So we have two altitudes given and one of the sides, the lengths of one of the sides. Now the question is, how do we attack problems like this in general? There are lots of methods that we could have and lots of places where we could start, but essentially it's usually a good rule of thumb. If we don't know where to start and we have a side available, a length of the side available, it's a good idea to just put the side somewhere and start off with the length of that side. So what we can do here is to just take the length of the side C, which we're going to use the lengths that I've put up here, and just push this line segment C somewhere else. All right, now I'll put it over here and just call this the line segment C. So we can say, starting right from the start here, that the two endpoints are already the vertices A and B. I don't know how familiar you are with GeoGebra as a tool. As I understand it, it's become fairly international now as a drawing tool for constructions of this type. What I will be doing in the constructions is I will be doing all of the constructions with the GeoGebra simply because the drawings are nice. I could have done them by hand on paper and used a camera to show them, but I think this is a nicer way to present. But of course, we have to be aware of the fact that in principle, a program like GeoGebra has more options than we actually want to use if we're talking about pure Euclidean constructions. A program like GeoGebra can do things that are beyond the capacity of Euclidean constructions. We can intersect lines, for instance, with curves of cubic equations or other much more complicated things than that. And that's something that we don't want to use now. So we will have to be aware at each step that we're actually doing things that can be replaced by simple straight edge and compass constructions. Now, simply drawing the length of a line is already pushing the envelope a little bit, because measurement is actually not allowed in Euclidean constructions in the proper sense. So actually what we're doing is we're just transferring the length of a given line segment. The length of the line segment C was simply given as in the drawing. And so we can transfer that to another line. We can do that with the compass, of course, but we are not allowed to measure anything. In classical Euclidean constructions, the only type of measurement, if we want to call it that, is simply the transferal of some kind of a unit that we can obtain from the drawing. So we can transfer that multiple times. We can also divide it into equal sections, either simply by dividing it in two parts with a bisector, which of course we can construct with straight edge and compass, or we can divide it into any other number of sections by applying similar triangles. That's always possible. But so essentially we can divide it into any rational ratio. And if we want any other things that aren't rational, then we have the option of doing constructions and applying Pythagoras, for instance, and so on. So there are options that we have. All of these things aren't going to be important for the constructions now. It's just important that we realize that we're limiting ourselves right now to strictly Euclidean constructions. Now, we need a next step. We have assumed now that we know where the vertices A and B of the triangle are. In order to finish our construction, we have to find out where the vertex C is. And we don't really know that yet, but we do know something about C. We know that the distances, the perpendicular distance of C to this line that contains the 2 points A and B is equal to this given distance HC. So what we can do now is we can construct by Euclidean methods the line parallel to this line segment AB in the distance HC. That's possible, of course, because we can simply take a point anywhere on AB. We can just take any random point. We can draw the perpendicular line here to the line AB. Again, I'm using a GeoGebra shortcut here. Of course, if we actually are doing a proper Euclidean construction, the right angle has to be constructed, and that takes several steps. We can't just assume that we put down some kind of a drawing implement and immediately have the right angle there. We have to do several steps. We have to use the compass to find 2 points that are equidistant from this point, and then change the size of the radius in the compass, and then again draw 2 arcs, and then let's find out where they intersect, and then join the lines, the 2 points to get the line, perpendicular line. That's all standard construction, but of course we're not going to worry about that now. We know that we're using a shortcut. We're using the GeoGebra shortcut to draw the perpendicular line, and we'll be doing that with our other constructions as well. But we have to realize that these are shortcuts for things that we could do with Euclidean methods. And now, of course, we can transfer this line, the length of this line segment, to this perpendicular. That's something we can do simply with the compass. We can take this length and transfer it over here with the circle. And if we intersect that with the line up here, we get a point that is on the this parallel. The distance from this point here to AB is, of course, equal to HC, because the length of this line segment is HC. So if we draw the parallel to AB, we have this line, and somewhere on this line, we will find the vertex C. But of course, right now, we don't know yet where it's going to be. It's somewhere on there. Now, in order to find where it is, we will need to apply some other idea that we have. And the other idea is now available by noting that the line segment HA, of which we are also given the length, is perpendicular to the side BC. So that means that the foot of this altitude here, this point that I'm pointing to right now, must lie somewhere on the semicircle with the diameter AB, because we already know that all points from which the segment AB is seen under a right angle lie on such a semicircle. So I simply need to draw the semicircle. Once again, I have a shortcut at my disposal here. I can simply draw a semicircle in GeoGebra. That's easier than actually doing construction. But of course, we know that we can find the midpoint of AB by Euclidean methods, and then we can draw the circle in that way. And by now finding the point that is the distance HA from A, which we can do by simply using our compass to transfer the length of this segment over to A with center A, we get the point here, which is the only option that we have for the foot of this altitude. So that means that this line segment here that we have denoted by HA here is the line segment that we have here now. This line segment, I'll make this red also so that we can see that. Okay, colors and let's just make it red so we can see that. So this red line segment is the same as this red line segment HA, and this foot is this point is the foot of the altitude on the side BC. So that means that this point must lie on the segment BC, and therefore we know the line that contains BC because it's simply the line joining B with this point. And that means that if we simply join these two by a line, we now know that C must lie on this line here. And since we also know that C lies on the parallel to AB through this other point that we've determined with the two right angles, we know that C must be the point where these two intersect. And we get the point C up here. And therefore we've completed our construction because we know that ABC, I'll just get rid of this and replace it with a line segment. And we maybe can make a little bit thicker. And hopefully that was not what I wanted it to happen, but there we are. And we can now replace these line segments by thicker segments just to show what we've done. So we've now found the triangle that we set out to construct. This triangle ABC has all of the properties that we wanted. The length of the side AB is equal to the given length C. The length of the altitude from A is equal to the given altitude HA, because we have this red line segment here and it's perpendicular to BC. And the altitude in C is equal to the given altitude HC, because all lines on this parallel have the same distance from the same perpendicular distance from AB. So we could also add the altitude here if we wanted to. Now this is a typical construction that is of the type that we'll be looking at also with the other constructions that I have prepared for today. It's the easiest of the ones that I want to show. It's not difficult to find this solution on your own, obviously, if you know all of the basic tools that are needed to do this. So it assumes some knowledge of what you can actually do with a straight edge and a compass. It assumes that you know a little bit about angles subtended over a diameter in a circle. So that's important, of course, to get a handle on the right angle that you have there. You have to know a little bit about the fact that all points on a line parallel to a line segment all have the same perpendicular distance, which is actually pretty obvious, but of course it's a fact that we needed to apply here. But if we combine these things properly, we can determine this solution. Obviously, we could now move this triangle ABC anywhere we want in the plane, or we could reflect it if we wanted to, and then move the reflection around, and we would have other solutions, but they're all identical in the sense that they're all congruent to each other. And that's really what we mean by saying that we have a unique solution in some sense to the problem. Some problems that can be set with other determinants may not be unique. They may have two solutions in some cases. There may be variants that are possible, but there are always things that are similar to this construction. And I've also already mentioned at the beginning, there are some things that simply can't be solved by Euclidean methods, where the steps that are required to finding the solution cannot be reduced to either linear or quadratic methods. And with Euclidean tools, we only have linear or quadratic methods at our disposal. Anything that we do with a straight edge is always intrinsically linear if we consider it to be from an algebraic standpoint, and anything we do with a compass is always intrinsically quadratic from an algebraic standpoint. So we can only solve problems that can be reduced algebraically to linear or quadratic equations and solving them in some way. Anything that can't be reduced in that way, it could be of a higher order, of course, but it has to be of a higher order that can be somehow reduced to elementary solutions of linear and quadratic problems. Okay, so that was our first problem that I wanted to have a look at. Now let's have a look at the second. The second, we don't need to save this, I don't think. Second one that I have was that was this one. This one here. So this is a second problem. Again, we have three determinants of the triangle ABC given, but it's of a completely different style. So the constructions that we will be using will also be quite different in many ways. It's maybe not much more difficult. It's probably also one of the medium difficult problems of this type that belong here, but we will see there's an extra added bonus in the middle where things become not so obvious and where we have to have some kind of an idea. So what we have given here is the in radius of a triangle ABC. We have over here in the little drawing that I've made, we have just a random triangle ABC. We have the in circle, so the radius of the in circle is rho, that's given. We have one of the x radii given, so we have one of the x circles here that also is tangent to the three sides of the triangle ABC. It's externally tangent to BC and internally tangent to the extensions of the sides AB and AC. And we have the radius here with rho A. And we also have the angle alpha, which is the angle that is opposite the side to which the x circle is tangent. Now, of course, we could also find a variation of this problem if we are given the in radius, an x radius, and one of the other two angles. The problem that results, or the solution that results, is actually quite similar. The actual construction ends up being slightly different, but if you can solve one of these problems, it's not difficult to solve the other. So the ideas involved are practically the same. So let's see how we can attack this problem. Here we don't have a side to start with, so we will have to start with something else. And here it seems to be reasonably obvious to start with the angle. We're not going to start with the radius or the circumradius, although one option would be to start with the in circle and then to see what happens. How can we fit this angle alpha knowing the in circle already? How can we have the sides AB and AC that would fit with such an in circle? But that's working in a way that turns out to be slightly more awkward from the constructions. It's possible. It's also possible to solve the problem in doing things in that order, but it seems slightly easier, slightly more more natural, I guess, is the word I'm looking for, to start with an angle. So what I'm going to do now is to simply assume that we have this angle alpha given somewhere. We'll just put this over here and say this is the angle alpha that we're given, and just say that this is already our vertex A of the triangle. Perhaps it's better if we move it over a little bit more. Maybe we shouldn't start that far over. Maybe here is better. We'll see in a second why. We'll need a little bit of space to move. Now, we don't know where the points B and C are yet, but we know that B is somewhere on this line and C is somewhere on this line. So it might be helpful if we extend the sides of this angle a little bit. So what I'm simply going to do here is now to choose a point here and then to extend this by putting in the whole ray up here and up here. That's just so that we have a slightly, or maybe I should actually not eliminate the point yet. We'll leave it for now. This is just so that we have the extensions and then see what happens. Now, we need to have some way to introduce the in radius and the x radius. And if we take a look at the little drawing that we have in the corner here, that's of course not to scale and has nothing to do with the actual lengths of the segments that we have given or anything like that, but it sort of gives us an idea of what's going on. We can recognize that we know that both the in-center and the x-center of the triangle, so the midpoints of these two circles here, they both lie on the angle bisector of the internal angle bisector of the triangle in A. So since we do know both of the legs of this angle here, we can also immediately construct the angle bisector. That's not a problem. And that way we will know we will know some information about where to put the midpoints of these circles. So we can definitely find the angle bisector. Again, this is one of the things where I have a shortcut. The GeoGebra allows me to simply draw the angle bisector right away by just marking points of the angle. That's something that we can construct, of course, with simple Euclidean methods by drawing an arc and so on. So I'm not going to worry about that now, but it takes several steps to draw it with a straight edge and a compass, and only one step to do it in GeoGebra. So again, once again, we're using a shortcut. Now I can actually get rid of these points here because we're not going to be using them anymore. But we have this angle bisector. And we know that both of these points lie on the angle bisector, and we actually can now determine where, start maybe with the in-center, where the in-center of the triangle ABC lies on the angle bisector, because we know that the distance of this point from either the side AB or the side AC, it doesn't matter which one we use, is equal to the in radius. And the in radius is given, that's this, the length of this line segment rho. Now, we already used in our last construction the fact that that means that the point must lie somewhere on the parallel to this, either the bottom line if we're using AB or otherwise AC, but I'm going to use the bottom line B, in the distance of which to AB is equal to rho. And we can find that by simply marking any random point here on the side. Then once again, as we did with the previous construction, drawing the perpendicular or constructing the perpendicular. On the perpendicular, we can simply use the compass to transfer the in radius up here. We get the point of intersection right here. So these lines intersect here, and we get the parallel to the bottom line right here. So that means that the in-center of the triangle will be right here where they intersect. So this point here is the in-center. Okay, sorry about that. I don't know why it did that. Sometimes when I click too fast on GeoGebra, it thinks that I'm doing several things at once, but that's just me working too fast. Okay, so here we have the point that is obviously going to be the in-center of the triangle ABC, because its distance from its perpendicular distance from the bottom leg of the angle alpha is equal to rho. Of course, this upper perpendicular distance is also equal to rho because it's on the angle bisector, and that means that we already know this point. And as the in-center of the triangle, I'm going to call it capital I. So this is the in-center here. And knowing the in-center, we also know the in-circle. So by simply transferring the radius here, I get the in-circle of the triangle. And we can see that it does indeed touch both of the legs of the angle as we claimed that it would. If we draw the perpendiculars, we can also find the points in which they touch, in which the tangent. That's not really important right now, but we could do that anytime. Now, similarly, we want to find this x circle here. And of course, we can find the x center of this point that we're going to call IA with exactly the same method, because the perpendicular distance of this point from the leg of the angle is equal to this given distance rho A. So we can do exactly the same thing. We already have a perpendicular here. We simply have to transfer this distance from here up to the angle, and it's going to move over a little bit. So I'm going to push this whole thing over slightly. This will prove helpful to us if we simply move all of this stuff over. No, this is not going to want to do that. We're just going to move the whole page over. So I have the x radius up here. So if I now draw the parallel, or no, first, sorry, the points in which they intersect, that's this point here, there. And now we draw the parallel through this point to the leg of the circle. We get the point in which they to intersect, and that is now going to be the in-center, the x-center, sorry, of the triangle on the side A. So we can call this point here IA. That's this point here. And once again, we can now draw the x circle that's implied by this, because we have this same radius and this midpoint. So that is the x circle. Now, knowing this, we still don't really know where the vertices of the triangle are. We're looking for the vertices B and C, and we somehow have to find these vertices B and C. And in order to do that, we need to find the side A, the side that's opposite the vertex capital A. And the side A is going to be tangent to both of these circles. Now, there are two options to find a tangent to both of these circles that is in the middle here. One can be slanted in this direction, and one can be slanted in this direction. By drawing both of these, we will get two solutions, but the two solutions are symmetrical with respect to the angle bisector in alpha. So we're actually still not getting two different solutions if we do this. But somehow we have to find these common tangents. And the problem is now, how do we actually construct such common tangents to two circles? Now, this is another construction that may be familiar, but constructing common tangents of circles is really not such a trivial matter. The idea is to understand that the two circles can be considered to be homothetic to each other, and finding the center of the homothety that maps one of the circles to the other. And there are two such centers. One of them is A, of course, because we have a homothety that extends the in-circle to the x-circle with the center A, but that's not useful because then we just get the common exterior tangents that we already know. But if we want the common internal tangent, we need the other common center of homothenty in here, and we have to somehow determine that. And in order to determine that, we need some points on the two circles that will map onto each other with such a homothenty. And the easiest way to do that is to simply use a point that's on the bottom and on the top of these two circles. That's what we can get in this way. So for instance, if we do the following, if we simply say we use the line perpendicular to the side here, sorry, I did not want to do that. Line, there we go. If we use this perpendicular, then we get the lowest point on the x circle. The lowest point on the x circle is where these two intersect. And on the other circle, on the in circle, this point will map to the highest point, because of course we have a horizontal tangent in this point, and we'll also have a horizontal tangent in this point. So if we simply draw the perpendicular here and intersect this perpendicular with the circle, sorry, that did not work properly. There we are, and we'll get this point here. And since this bottom point of the X circle maps onto the top point of the in circle with the homothency that we want to use, we simply have to join these 2 points, and we'll get the center of the homothency that we need on the angle bisector, of course, because the midpoints map onto each other. So by simply intersecting the this line segment with the angle bisector, we get the center of homothency. Now, by constructing the tangent from this point onto one of these 2 circles, either of the 2 circles, we'll get the line that contains the 2 points B and C, because then we'll get a tangent of one of the circles, and that's automatically a tangent of the other circle. And by simply intersecting that common tangent with the 2 legs of the angle that we already have in alpha here, we will get the 2 points B and C. And that's very easy to do. We know that the radius of a circle is always at right angles to the tangent. So using that perpendicularity, we simply, once again, you draw a semicircle here, and intersecting the semicircle with this small circle here, we immediately get the point where the this radius here will be tangent to the line that we can draw here, and so that it's perpendicular, so therefore that's the tangent. And that means that the tangent of the circle through this point is simply this line here. The line that I've constructed now is indeed a tangent of the in circle and also of the X circle. As we can see here, we could find the point of tangency there easily by drawing a line perpendicular from IA, but we don't need that. We only need the other 2 common points B and C. So we have one of the vertices of the triangle up here and one of the vertices of the triangle down here. Which one is B and which one is C is now a matter of taste, I suppose, but by naming the points in counterclockwise order, which is, I guess, more standard than the other way around, well, we would get point B down there and point C up here. So that finishes our second construction. We have a triangle ABC, which, as I said, is uniquely determined for the simple reason that the second solution that we get, which of course would be with the other tangent that we can draw from the center of homothency here to either of the circles, is symmetric with respect to the angle bisector and therefore congruent to this solution. It's just on the other side, but it's for our purposes, it's an identical solution because of the symmetry. So we have this second problem also solved. Now, since we only have a limited amount of time left here, I do have more problems prepared, but we don't have the time to do all of the things that I have prepared. But I'd like to show one more construction, which I think is a lot of fun, because it's something that is normally not considered to be an obvious construction at all. And that is the following. We'll open up this file. We don't need to save this. We'll open up this one. So what we have given here is the length of the 3 line segments joining the 3 vertices of a triangle to the midpoints of the opposite sides. And we know that the medians of a triangle intersect in the centroid of the triangle. So these 3 line segments will intersect in the centroid. And as I already mentioned when we were talking about the tools at the beginning, the centroid always divides each of these median segments into sections that where the longer one, the one pointing toward the vertex of the triangle, is twice the length of the shorter one pointing toward the midpoint of the opposite side. So we're essentially dividing each of these medians into 3 segments of equal length by use of the centroid. Now, that's an interesting fact, and as you can see by what I've noted up here, I've said, okay, we're given the length of the 3 median segments that we have here, and I've already divided them into sections that will divide it into thirds. So this segment here on SA is half the length of the other segment, and the same for SB and SC. But how can we find a triangle that has the lengths of these line segments as the lengths of its median segments? By simple Euclidean methods. That's not obvious at all. How are we supposed to start a construction of this type if we don't really know what to do with these things? So we have to find some kind of a construction where we can do something. Now, in order to start off such a thing, we will have to start with some knowledge of something. And right now, we don't really know anything. We don't know any of the vertices of the triangle or anything else. But we can assume maybe that we know one vertex somewhere. So let's start off just by assuming that one of the vertices is here. And let's assume that maybe this is the vertex C. I could have chosen any one of them. It doesn't matter really, because of course the given segments are completely symmetric. We have all 3 equally well known. And also, we can assume without any real loss of generality, because we can move these things around any way that we want to, that we also know the line that contains the median through C. So I can just draw any line through C, and I can just assume that this is going to be the line that contains the median through C. And if that's the case, then I already know how long this segment SC is, and I also know the distance from C to the centroid of the triangle, because that's 2/3 of this. So if I transfer 2/3 of the length of the line segment, SC, which I already have here, of course, we can divide that into 3 sections by using similar triangles with plain Euclidean methods. So that's something that we can do with Euclidean methods, is divide a line segment into 3 sections of equal length. But by simply transferring this line segment down here, we will get the position of the centroid of the triangle here. And in our typical notation that we would use here, I would call that this point S. I know that calling the centroid S is also one of these things that is not completely standard, but as I said, this is the what we would normally call it in the notation that we use here in Austria. So that's why I'm just going to use it here, and then we can eliminate the circle again for now, just because it's in the way. I don't really need this. I only needed the circle to transfer the length of this segment, and that's just something that I can do with the compass as a tool. Now, of course, I can also find the end point here. That's the midpoint of the side AB by transferring the smaller section in the same way. So simply by taking this section and transferring it over here, I will get the midpoint of the side AB, and I can actually maybe name this. That might turn out to be useful. I'll just name this MAB, just so that we know for further reference that this is actually the midpoint of, oh, sorry, I made a mistake here. There we go. That was just a typo. There we are. That's the midpoint of the line segment AB. But otherwise, we don't really have any further information. We know that this is the vertex C, and because of that, we know that this is going to be the centroid of the triangle, and the other 2 of medians will also pass through this, and will also be divided into thirds by this. But otherwise, we don't know the angles, so we don't know how we're supposed to draw these. But okay, and this is going to be the midpoint. Now, there is one other chunk of information, of course, that we do have that will prove useful. We know that the distance of A to the centroid will be 2/3 of the length of the median SA. And we know that 2/3 of SA, that is this distance here. So that means that the point A will lie somewhere on the circle with midpoint S and with this radius here. So that means that I can use the compass to transfer this line, the length of this line segment here to S, and I obtain this circle here. And this circle has the property that the point A must lie on that somewhere. So it's maybe useful if I call this circle CA. It's a circle with, so that's why I circled C, with the property that A lies somewhere on the circle, for sure. Similarly, I also know that the point B, the distance of the point B from the centroid is given by 2/3 of the length of the median that I have here with SB. So that means I also know a circle where the point B must lie in a similar way. I can use my compass to transfer 2/3 of the length of this median to S, and I get a second circle. And this circle has the property that the point B must lie on it somewhere. So I can call this circle here CB. So B lies somewhere on CB and A lies somewhere on CA. I know that. In order to actually find out where A and B lie now, we can use the following idea. The distance from the midpoint MAB to A and to B is equal. That means that if I reflect the point B on MAB, I get the point A. I can simply do a point reflection of B onto with this center onto A. I could also call that a rotation by 180 degrees. It would be the same thing. Rotating by 180 degrees would also result in the point A, but that's of course the same thing as a point reflection. So there's no difference. That means the following. I know that B lies somewhere on CB. So if I now reflect the whole circle CB on the midpoint MAB, I will get the possible spots where A could come to lie, assuming that B lies somewhere on CB, and of course A has to lie somewhere on this reflected circle, but also A has to lie somewhere on CA. So I know that A must lie on two different circles, so it must be one of the two common points of these two circles. So all I need to do in order to do this now is simply to reflect CB on MAB, and I get this circle here. And that means that A has to be one of the two common points of this reflected circle here, which is now the symmetrical circle to CB with respect to MAB. And it must also lie on CA somewhere. So if I intersect these two circles, this one and this one, I get two possible spots where the point A could lie. Of course, we don't know which one it is, but it doesn't really matter because we get two solutions, and the two solutions are symmetrical with line CS that I assumed right at the beginning. So once again, we're only essentially getting one solution. It looks like we're getting symmetrical again, and therefore congruent. So for practical purposes, once again, we're only getting one solution. I'll simply assume that one of these is A. We'll take the one on the left. And that means that the point B can now be determined in two different ways. I could simply reflect A on MAB. I'll get this other point on CB, of course, and then this has to be the point B. If I'm going to be constructing this with my straight edge, this tool that I'm using here in GeoGebra, of course, then I would simply use the straight edge, draw the line connecting an MAB and intersect with the circle CB that I already know. So that means that we now have the triangle ABC. And once again, and for some reason, this is the triangle, the properties that I wanted. If I now of BC, I can do that simply by, again, I have a shortcut here by simply using midpoint. And I now can connect A and this midpoint. That's the midpoint. I don't want that. I wanted the line segment. There we are. Then the length of this segment, sorry, excuse me, is equal to, excuse me again, is simply equal to the given length SA. And I can do the same thing from B. If I find the midpoint of AC and connect it with B, the length of that segment will be the same as the given length SB. So I have actually constructed a triangle from the length of the three median segments that are given. Now, as I already mentioned, I have some other things prepared. Maybe we can have some options, since we've used up our time. We can have some options where I can give these to you online, and maybe you would like to try your hand at this construction. The other two that I have are actually not at all easy to find the solutions to, but I would encourage you, if you have the options to do this, I can upload them somewhere if I'm given the option to upload these, and then you can try doing the constructions yourself, either on GeoGebra yourself. I don't know if you're familiar with the program, but it's open source. It's available freely. You don't have to pay anything to be able to use GeoGebra. You just go to the website geogebra.org and get the software, and you can immediately start doing constructions in the software, or otherwise, of course, you could copy and draw it with actual physical straight edge and compass. And that, I guess, brings us to the end of what we're doing here. I'll return to this here and show you what we are showing here. I have some, as it already says, I have some more information. If you are interested in some of the other things that I do and that I work on and that I'm involved with, this is my personal website. If you go to my personal website, you'll find versions in German and in English, where you can find all kinds also of links to things that are very useful for mathematics and for preparing for mathematical competitions, information about competitions, information about mathematical backgrounds, also various papers that I've written over the years and so on. And if you're specifically interested in the kind of thing that we were talking about today, this link here will lead you to a project of the University of Vienna here in Austria. The materials here are all in German, so that may be a difficulty for you, but because it's all geometry, and of course it's all about geometric constructions here. If you look at this, the drawings are of course independent of a language, and so you can have a look at these things. The materials that I've presented today are also available here, but a lot more is there. This is the project of the University of Vienna is one that I have also been involved with for the past year and a half. And my part in this project is developing materials that have to do, among other things, of course, that have to do with various constructions, geometrical constructions, not just triangle constructions. There's a lengthy section on ellipse constructions. So if you're interested in conics and constructions that have to do with conics, that's still in development. The ellipse section is done. Right now I'm working on the parabola, and there's still a section on the hyperbola come. Those things will be available by summer, I hope. And there are a lot more materials available that I think you'll find very interesting at this website. And so at the end, all that's left for me is to thank you for listening. I hope the things that I was able to show in this hour, slightly more than an hour, I guess now, were interesting for you. I hope there was nothing too trivial. I hope there was something that everybody found new in some way, at least. Finding these constructions for slightly obscure combinations of given things that we can know about a triangle in advance, I think is always quite a fascinating thing, and it's an enjoyable thing where you can use all kinds of tools from elementary geometry. And it's actually surprising how many of the essential elementary tools that you would need to prove even high-level Olympiad style problems from elementary geometry are required in something as seemingly elementary as triangle constructions. We've only scratched the surface here, of course, with 3 constructions that I was able to show. Okay, I suppose that's it for now, and I'm ready for any questions or comments you might have.
Thank you, Robert. It was a really great session. I too found it really interesting. Although some things are really complicated, I was able to get through with it. I did get to learn new things. And the resources that you mentioned, we will make that available for everybody. So I will get back to you through email. Now
Yes, I'll
let's
simply send you all of the material, and you can upload them however you see proper.
yes, thank you very much. Now I would like the audience to please ask their questions. If not, we have some prepared questions that was asked in the Google form. Please, if anybody in the audience wants to ask a question, you may drop them in the chat. I guess not. So the first question I will put it in the chat. Robert, if you look at the chat, there's a question.
Yes.
Please.
Inner circle and outer circle inverted. Yes, the Steiner chain. Well, the nice thing about the Steiner chain is that there's a whole row of circles that that are tangent to each other, one after another, and that are internal to a specific circle and external to another circular arc. And the idea of the inversion that is here is that the inversion makes it possible for all of these circles that are tangent one after the other, that they all have the same radius. So therefore, their midpoints all lie on the concentric circle to the other two circles that simply has whose radius is the arithmetic mean of the larger and the smaller circle. So the idea is simply using the concept of inversion to actually find this very specific possible version of these other circles. Inversion as a tool is, of course, an excellent tool for all kinds of proofs and all kinds of constructions and all kinds of different things that you want to do, because of course inversion makes it possible for a circle to be mapped onto a straight line. So that means that sometimes things that are awkward, different issues of tangency or issues of intersection, can be reduced in constructions to things where we don't have to worry about intersections with circles, but simply are intersecting straight lines. That makes things easier. Also, we have things, as mentioned here, with the Steiner proof, where we have the option of having two circles that have just general common or relative positions to the very specific relative position of them being concentric, and that has huge advantages as well for certain types of constructions. So the Steiner chain is something that is maybe not really useful, but it's a fascinating picture, of course, once you've seen the things. I don't have any pictures prepared right now of it, but it's definitely worth having a look at. And it's also worth noting that the idea of Steiner chains is something that different cultures have found over the centuries independently of each other. I'm very well aware of completely independent developments of Steiner chains, of circles being developed in the European tradition of elementary geometry, and I know of specific spots where this turns up in the Japanese classical tradition of elementary geometry, in the classical sangaku that's developed in Japan, completely independent of other countries' mathematical traditions. And as far as I know, I'm not 100% certain of this, but I think that the Steiner chain is also something that was independently discovered in some Central Asian traditions, perhaps Chinese, perhaps Indian. I'm not completely sure where these things are, because in those cases I'm not 100% aware of the material where I would source it, but I do know of the European tradition and of the Japanese tradition. So it's quite a fascinating topic. It's interesting that you bring that up in this context.
Yeah, thank you very much. There's another question, if you could see the chat.
Okay, yes, the idea of doing constructions without knowing the jargon. Yes, I would say yes. The main important thing of doing constructions is actually something that you do by applying the tools in an allowed way. And that's something that is actually independent, I would say, even of language. Not only do you not need to know the jargon, you don't need to be able to formulate what you're doing. It's very possible to simply feel that you have the tools in your hand, and because of course you can draw a line, and you know a method for instance constructing a right angle, because you know that you simply take the compass and draw a point, and then draw an arc, and then stick the compass into the 2 points that result, and draw 2 more arcs, and then you get a line that's perpendicular, and so on. You memorize these construction steps as activities, as things that you do completely independent of language. And therefore, the jargon is actually, I think, not necessary at all. The only point where you would require the jargon is, and the specific terms that are specific to those activities, is if you were in a position where you wanted to explain a construction, for instance, in a mathematics competition. There are still some competitions, it's less common than it used to be, but they're still around, where the geometric construction is required to solve a problem. Are asked to solve a construction by developing, or to solve a geometrical problem by developing a construction, then it is necessary to be able to explain, maybe not in words, but at least in some kind of shorthand, in some kind of mathematical standardized shorthand, what the steps of the construction involve. Of course, it's always helpful to learn terms, but it's not necessary to do the construction, certainly not.
Thank you for that. So is there something wrong about the Euclid's element? Wrong about it?
I would say no. There's an excellent thing about Euclid's element, because they were so complete and so correct in their way that we are still able now to questions that it was very worthwhile for me. I did read them in both in English and in German translations, and it's fascinating to see how the constructions and the elementary axiomatic in elementary geometry included in the elements are contained in this in such an old body of work. The thing that you might consider is that there were certain aspects that were not dealt with, of course, that were still open. But of course, at least with any, there are always additional questions, there are always more things done after the work. A question, for instance, of the parallel axiom was legitimate or not, or whether it followed axioms and so on. That question, of course, propelled mathematical inquiry and mathematical research for centuries. I guess even up until the 18th century. Now the problems resulting from inquiries into the parallel dealt with and solved. And because, of course, we know now about non-Euclidean geometries where the not hold, and of course we know about geometry where for model describe reality, to describe Euclidean geometry. But that doesn't mean that the models from the elements are in any way wrong or bad. They're simply abstract, and they are even good models for physical reality as long as we stick to a macro world, to the world that we live in, to things that we can see from our own rooms or just walking around in the world. As soon as things go to a cosmological level, if we're considering the universe, or if we go to a subatomic level, then obviously Euclidean geometry doesn't work. But at a macro level, Euclidean geometry is perfect, and the things in Euclid's elements are even well worth studying today.
Thank you very much. That was very informative. There was a lot of information. What is projective geometry?
Projective geometry. Okay, projective geometry is the extension of Euclidean geometry by adding the concept of a point at infinity. So if we consider the concept of parallel lines in Euclidean geometry, and Euclidean, well, starting from the Euclidean plane, of course, we can go in higher dimensions. But we can define the concept of infinity by saying that parallel lines intersect at a new point at the point at infinity of those parallel lines, and we say that we can join any of the regular points to a point at infinity, constructing in parallel to one line that points in that direction through that point. Of course, that assumes the Euclidean parallel axiom that I was talking about earlier, the fifth axiom. And if we assume that holds, then we can also call the set of all these points of infinities the line at infinity. And by simply adding these new points and this new line to the points and lines that we have in the Euclidean plane, we obtain a new plane that we call the projective plane. And the geometry in this projective plane is then projective geometry. The advantage of considering the projective plane over the Euclidean plane is that in the projective plane, we don't have to differentiate between joining two actual points and finding the line joining two points, or joining a point and a point at infinity, which implies, again, the parallel axiom. So finding a line parallel to a different line through a point, that becomes the same thing as simply joining 2 points. And also we can assume then in the projective plane that any two lines always, and two different lines, always have a unique point of intersection. There's no such thing as parallelity anymore. So that means that they can intersect in a finite point or at a point at infinity, but they will always intersect in a unique point. And that simplifies things. So using that, we can introduce various types of mappings that also we could introduce in the Euclidean plane, but they're much more complicated to introduce in the Euclidean plane. They're much more elementary to introduce in the projective plane. And these results are then independent of whether we have parallelity or not, because parallel lines are simply points that intersect at infinity. They intersect the same as any other lines would. And so we don't have to differentiate. It simplifies things a lot. So projective geometry is essentially in that sense, and that I think is the most important sense for school geometry, for competition mathematics. In that sense, it's simply an extension of Euclidean geometry, but at the same time also in some ways a simplification. It makes life easier.
Thank you very much for the answer. The next question is a closed subject.
Closed? I guess that depends on on what you consider to be closed. I think it's generally considered to be closed research subject in the sense that you would consider higher level mathematical research to still have questions open. So there are no big questions open in Euclidean geometry that people would spend their whole careers working to figure out. But I would say it's not at all a closed subject in the sense that there are a lot of details to be found. And in that sense, there is, and the difficulty of these details can be incredible. So there's a lot to be discovered in Euclidean geometry that's not known, I think. But in the sense of a very abstract research area, it would probably be considered a closed subject for most research mathematicians that work at such an abstract level. I don't think you're likely to win an Abel Prize or something like that for research in Euclidean geometry anymore. I don't think there are any big open questions that can be solved of that type.
Thank you for that answer. This will be the last question for today. I'll put it in the chat. How are Olympiad problems made? How can I be a better problem solver? And how can I master the basics? How can I make my own problems? Somebody wants to make their own questions.
That's an excellent problem, and it's a very wide-ranging problem. It's of course, as anybody can imagine right away, not something that I can answer with just 2 sentences. Becoming a better problem solver, that happens through studying problems, studying solutions, studying more theory, of course, and solving as many problems as possible. So as with anything, practice is what makes the big difference. Just studying as much as you possibly can will definitely help. Mastering the basics really means figuring out what the basics are. And that's not really all that easy because there's a fairly wide range of what you can consider to be basic in Olympiad problem solving. I guess a good place to start with anything, apart from of course, there are books, there's a lot of literature available, but a good place to start if you're looking for online resources, just by the computer, is to have a look at Art of Problem Solving, which of course I'm sure a lot of people here are familiar with. It's an international resource that has all kinds of information about competition style mathematics, and it has sections devoted to all of the different styles of things. The real basics to master that you have to start with for Olympiad problem solving are surprisingly few. But on the other hand, by attacking harder and harder problems, you find that there are more and more things that you can consider to be considered basic if you advance to harder problems. So really mastering that, again, involves just more practice and more reading and more study. The best thing is to really have a look at the existing literature and solving problems by yourself, but also reading finished solutions by authors. Developing your own problems and finding problems, now that is a huge area that is really hard to describe. New problems of a very can generally just develop by developing very exciting things. But the question is, how do you find new difficult problems, new higher level problems? And that there are usually 2 typical methods that are used for that by people who develop Olympiad problems. I do that as well, of course, and others. There are usually 2 ways that you can find things. One is to take well-known problem types or a well-known result of some kind or something like that, and finding a variant. A variant could be something either easier or more difficult that you can find by either generalizing in some way or but making something more specific. So it can go in either direction. The generalization could be, for instance, if you have a problem that holds, say we're doing some geometric problems now, and it holds for, you know that something holds for a right angle triangle, then you can have a look at, okay, what if we loosen the restriction of the right angle and say that the angle is not a right angle, it's an acute angle now, and what happens then with the result? Can we still prove something similar, something analogous, or not? Is that even true then? Or what other things can we assume? What if we assume some other specific angle? What if we assume instead of 90 degrees, I don't know, 60 degrees or something like that? What will happen in that case? So that's one option, either generalizing or making more specific. The other thing is that a lot of Olympiad problems result from research mathematics by finding a specific case, excuse me, a specific case of something that results in research mathematics, in general research at university level, at the level of the highest type of research that there is, because typically during general level mathematical research, some questions will be asked or will pop up that haven't been asked yet. And during the research itself, they will probably be of a too complex level to make a good Olympiad problem. But there may be a special case for such a general research problem that is relevant for an Olympiad problem. So maybe, for instance, if something in research involves, I don't know, some kind of a general vector space, an n-dimensional vector space, and the proof is done in quite a general way, and then it's reduced to the case where to have a two-dimensional vector space where we just have a plain geometric result, that may be a new result. It may be that if you reduce it to a two-dimensional result, then the result is already well known. So then it's not interesting. But sometimes such problems that are interesting because of general research will reduce to a two-dimensional simple case that is not that well known. And so then there may be some very elementary proof for this so far unknown fact that can be found then by considering it sufficiently. So that's another way that Olympiad problems often are developed. Geometry maybe not quite as often as one would like, but that's a very common path for instance, IMO problems at the International Math Olympiad to be created in the areas of both number theory and combinatorics. A lot of the combinatorics problems and a lot of the number theory problems that pop up there are actually special cases of things that result from research mathematics. Now, making your own problems, if you really want to do that, I would suggest going for it, because that is also a good way of improving your own problem solving skills. Developing your own problems and solving problems that you've set yourself, and also finding the limits of that, finding where you've set a problem and thought of an idea of a concept that you maybe have difficulty proving, and then trying to find out whether it's even possible to prove it. It may be that you just don't have the tools at your disposal yet, but you can find those tools, you can develop them. Or otherwise, discovering that the problem can't be solved by elementary methods, or maybe can't be solved at all. That's all of those things are interesting, and all of those things will also improve your own capabilities. So yes, I would definitely suggest making your own problems, but again, you can do it by taking a problem that you already know, finding a variant, consider some number or some situation and changing it, make it harder, make it more easy, and see if you can solve that.
Thank you for your advice. That was very insightful. We are now approaching the end. This recorded session will be available in our platforms, social media platforms, and our YouTube channel. And you may also request us for the video. We will provide it to you. And the resources the other resources Robert had to share, we will also make that available in our social media. I would like to invite Chandan to thank our guest and thank our audience.
Sure, Prashant. Thank you so much, Robert sir, for like not just from the behalf of MIN, but from our whole country, for your valuable time, and the knowledge that you share today. And thanks everyone in this Zoom meet for being part.
Thank you very much for
Prashant,
inviting me. It was an honor and a privilege to be able to do this, and enjoyable very much for me.
yeah,
Thank you.
it was. Prashant,
Yes, it is for us too. I hope we will stay in touch, and maybe sometime later we can get to learn more new things from you. I will end this meeting now. Thank you very much again.
Thank you.